to start with the exercise we had last time. And I see now that we had 84% of the students who responded accurately, and that's pretty good. This is very good, and I'm very happy about it. At the same time, what I've noticed is that there is a large number of students who have not responded to the question at all, who have not tried to do this exercise. We have, I believe, the number of students now in the class registered are above 55. And so there are a few of them who have not tried. So I think that it's just an opportunity. It's just missing points, I think, for those who have not tried to do it. And just, the opportunity to get a few points and learn also. That also brings me to just talking about the makeup assignment, which I'm going to give this coming weekend. Whoever wants to take it and has the reasons, the appropriate reasons, I will have I will tell you when it's going to turn on and when is going to be do. Is going to practically be close to an hour, and will be a top hat like quiz, because most of the students, if not 100% of them, who would like to take it is because they've missed top hat, because they for valid reasons, obviously. So it's going to be a top hat type of a quiz. It will have questions, and you will have to answer them. You may have to do some work on the side. If you would like to provide me with your work in case you are not sure about your final result, I will be willing to look at it. But it's going to be like a quiz. It's gonna be practically more than one quiz, because some students have a number of points to capture. And so that's what I wanted to say. And I would like to hear any comments or concerns about that. I will distribute it on Saturday or Sunday. I don't know which of the 2 days you prefer. I was thinking maybe Sunday is better, because Saturday many of you are involved in different types of activities. And unless I hear some objections, it's going to be on Sunday from 2 to 3. I will send you a couple of announcements to remind you. And I will just, it's like top hat as I do now. I will release it at 2, and then the deadline is going to be 3 p.m.
Just to be clear on that, this is only for people that have like university excused reasons to make a point.
Yes.
Okay, thank you.
And as I said, yes. And as I said, those who responded to me that they needed to take it were individual. All of them had missed, or not the majority of them, I would say, if it's at most one person. And I don't even believe, I think everybody has missed exercises or quizzes that we have distributed using Top Hat. So that's what I decided to give it in that way. We are not going to have an exercise today. I will have a quiz for you on Friday. But today, what I wanted to do, the other specific questions, I wanted to start with a problem that we did last time. I will do a quick review from the beginning. And then what I wanted to do, what I decided to do, is to give you some explicit guidance on how you're going to do how you're going to put together the solution of these problems. At this moment, you need to understand we are at the point where we do true design on an amplifier because we are trying to optimize between noise, where we try to reduce noise to the minimum, and gain, where we try to increase gain to the maximum. And what we said last time is that the two do not go together. Minimum noise does not mean maximum gain. As you will see, they are conflicting parameters. So we try, as we try to reduce one, which is noise, the more you try to reduce the noise, the lower your gain. And so usually we want minimum noise and maximum gain, but as you try to go low in noise, you go low in gain, and then that is not the direction we would like to take. So you always try to find an optimum point. Sometimes you do have guidance how to define this optimum point, like you will see in this example. Some other times you don't. People will not necessarily tell you. I will point to those places where you have guidance and to those places where you don't. But what I decided to do is to give you the process step by step, so you organize it better in your mind. And because what we said, this is a true recipe, really. What you need to remember from the physical perspective point of view is that when you design a low noise amplifier, you're not going to be able to have a very high gain. Usually your gain is going to be compromised. Also, a low noise amplifier is not going to give you a lot of power for the same reason, obviously, all right? So reduced gain means reduced power. So usually low noise amplifiers are there to in your system. If you remember, they're very early, right after the antenna, because with low noise, you have a filter, first of all, to cut all of the unwanted frequencies and all of the noise that is outside of your band. And then whatever you keep after the filter, because it comes at a very weak, the signal is very weak, then you have to amplify, but you don't want to introduce more noise that already has. So that's where we put a low noise amplifier. So we amplify, it is a modest amplification, considering how high of a gain we could have. So it's modest amplification, but it's very low noise. And then from there on, we take it and then we process it, either we mix it, we down convert it rather, and then you may do more filtering and more amplification. And the lower the noise in the signal, the more the gain you can put in the amplifier. So these are the fundamentals, all right, as we think of the design. So when the other thing we discussed, when somebody wants you to design a low noise amplifier, they will come with very specific characteristics for the transistor that the maker of the transistor has specified. And what are those? Is the minimum gain, minimum noise that can be provided by this transistor, and whether it's going to be provided or not depends, of course, a lot on how you design it, but it's the capability of the transistor to provide that minimum noise is there. Then they will give you the equivalent noise resistance, and they will give you an optimum admittance, which in fact is it represents, as it says here, the optimum value of your source admittance to be able to create the lowest possible noise figure. So the other thing that we mentioned last time is everything that has to do with noise
Dr.
is on the front part of the amplifier. Yes, what is your question?
Why should be admittance, not impedance?
You can do admittance or impedance, but they are using it in this form because of the formulas.
Okay.
All right. I mean, we go, if you remember, we go from impedances to admittances. Sometimes you may see formulas with the impedances, some other times you see them with admittances. I mean, however, the expressions are given. But you can go from one to another, no problem, all right, as we know, whether you are in an equation or whether you're on the Smith chart. So we can speak about an optimum source admittance or an optimum source impedance. Here, for example, I talked about an impedance, even if I have it in an admittance form. Okay, so it's not wrong to do it as long as you know not to mix up when you're using them, all right? So I will put here this because it's not exactly an impedance, or you can have a Z optimum here if you want to be consistent, all right? You can say, okay, I will put here Z optimum, and what is Z optimum here is 1 over Y optimum. And why did I use Y optimum? Because that's how the expression is in the book. And I'm going to follow the book, all right, obviously. So when you see something written in my notes, you can correlate that with what is written in the book.
I have a question.
Yes.
I'm a bit confused. So the optimal impedance give you the minimum noise or the optimum noise?
Optimum is minimum. The optimum noise in a low noise amplifier is the minimum noise.
What
right?
about our gain would be in this case?
Gain, the optimum gain is maximum gain. So you always need to remember, when it comes to noise, you want to minimize it. When it comes to gain, you want to maximize.
Yeah, so but you said we can't have minimum noise with the maximum.
Yes, but when I speak about optimum, in each one of them, there's not optimum together.
Oh,
but
okay.
Optimum in each one of them, when I speak about optimum source impedance, it means minimum. When I say about optimum noise, if I use that word, it means, or if anybody else uses it, it means minimum noise.
I see. It's just optimum for the noise, not the whole the both of them.
Not both of them, right?
I see. Okay, thank you.
Yes. Okay. So now, this in fact, just to introduce us to the formulas here. So if I had an optimum reflection coefficient on the front end, and then you see this here, and that implies that my source will have a value that will give me a minimum noise. If I had that, practically you can see it. If my gamma sub S, which is here, you remember, I'm not gonna show this all the time, but I wanna show it here now. Look where gamma sub S is. Gamma sub S is this one, you need to remember. When we speak about noise, it's only this part that we are concerned with. All right, gain, of course, is everything. Is this, and is this, and is that. And the product of the three gains gives us the total gain. But when it comes to noise, is only this part. So gamma sub S is the reflection coefficient I see when I look towards the source. So I'm here, and I'm at this point, here, and I look towards the source, like this. The source is here. All right. Okay. So now what do I have here in equation 1? I have an expression for the noise. If this noise is not the minimum, what we see it, when is this happening? When my gamma S does not have the optimum value. Optimum is when your noise is minimum. And it shows from here, if your gamma S is equal to this optimum, whatever we call optimum, then according to this expression here, your F equals F minimum, okay? And then if your gamma S goes away from this optimum, you're gonna see that in fact a lot more on the Smith chart, then practically you start deviating, you go away from the minimum noise and your noise increases. That's what it shows. Expression 1 shows that your noise increases as your gamma S moves away from the optimum, okay? And then from there, we identify these noise parameters. Just a parameter is a way of, it's helping us to develop the circles. We define this noise parameter, and then on the basis of that, now we have two equations, 4A and 4B. These equations are important because why? It shows that all the points, gamma S, so we are looking at gamma S, all of the reflection coefficient possible values as you look towards your source are on the perimetry of a circle, where the center of the circle is C sub F, is given by this expression, and the radius of the circle is given by that second expression. So all of the gamma S values, possible values that give the same noise, are on one circle. Therefore, since there are possible many different noise values you can get, each noise value, it's F here, it's F here, will give you one circle. And what are these points on the circle? They are the possible gamma S reflection coefficients. Okay, now that's what you keep in mind, all right? This is the whole theory behind the problem. We will try to solve the problem below, and I have given you this example that we talked about last time, and we're gonna complete it today. And I wanted, before we go there, to say, okay, if I do whatever I do, which we're gonna describe right now, and I find my gamma S, then how do I go there to find gamma L? Because I still have to design the output matching network. How to find gamma L? From the expressions of gamma out, if you remember, and then you're going to see them later, because we are repeating them here for you to remember. When we spoke about gain, then we spoke about gamma in and gamma out. When we spoke about maximum available gain, we said that gamma in was the complex conjugate of gamma S. And then we said that gamma out was the complex conjugate of gamma L. All right, that was for maximum available gain. Now, since our gamma S is going to be determined by the noise that we would like to have, how are we going to determine gamma L? From the same expression as we did before. So even if gamma S is determined by the noise, gamma L is still going to be the complex conjugate of gamma out. And for gamma out, there are expressions that will give you gamma out in terms of gamma S. So the moment we know gamma S and we determine it from noise, then we know gamma out. And as soon as we know gamma out, then we know gamma L from the complex conjugate. Is that clear? All right. Now, here is the problem that I'm giving. Last time the same. BJT, somebody measured it, obviously made it and measured it. And they gave us all the characteristics. Scattering parameters, they gave us F minimum here. They gave us gamma optimum here. They gave us the noise resistance there. And what they told us is we want to design it so our F does not go above 3 dB. When I say F max, that means I cannot tolerate a noise figure that is above 3 dB. And gamma minimum is going to be 12 dBs. I cannot tolerate a gain that is below 12 dBs. Do you understand those two together?
Yes.
Okay. So now, how are we going to solve this problem? There are 6 steps you guys have to follow. And I outlined them here, and we'll take one step at a time. And this is the process. You're not going to change no matter what when you try to design. Step number one, you will have to check if this transistor can be considered to be unilateral. Why is that? Because when you have a unilateral transistor, then the expressions become very simple. So you would like to simplify your life, all right? So you will check if you can do, if you can assume that S12 is 0, because always S12 in a good transistor is going to be small, but you don't know whether you can ignore it. All right, so you have to test for it. So step number one. Step number two, after you find S12, then you have to understand how much is your maximum available transducer gain. You want to know, so how inherently, how high of a gain your transistor could give. Why is that? Because if you tell me that my minimum value of the gain here can be 12 dBs, and the maximum that can be provided by the transistor is 12.5, then I'm in serious trouble. Because to go, if the maximum possible is 12.5, you're asking me to do 12 dBs. And at the same time, you're asking me to go only 1 or half a dB above the minimum noise. Well, that you can go without wasting your time. You can go back to the person who asked you to design it and say, I cannot do this, before you go and waste your time to find how to do it, because it's not going to happen. So you always want to know what is your minimum noise, which here they gave it to us 2.5 dBs, but you also want to know how is your maximum gain that you could get from the transistor, which they have not given it to us. They may give it to you, but here they have not given it. So you have to find it. That was step two. Step three, after you do 1 and 2, then you have to go and plot the constant noise circles using the expressions we had before. Then you plot them on the Smith chart. You keep them there. Then you go and plot the constant GS circles, not the total GT, not the total gain for the amplifier that includes the front, the transistor, and the back end, but only the gain of the front end, which is the matching network. You want to plot those. From those and how those intersect with the noise circles, we identify the gamma S that we are going to go for. And after we have the gamma S, we identify the gamma L. These are all of the 6 steps that you will have to follow in any low noise amplifier design. Okay, any questions about that before we start? We start with each step at a time.
If we presume the unilateral case, then we know that RL will be S22. So if step 1 holds, can we just define RL right after step step 1?
Yes,
okay.
Exactly. And that's what it does when you go unilateral, that it simplifies a lot of things. If you can go unilateral, you simplify a lot of things. If you cannot go, however, all right, what are you going to do? You know, do the best you can and bite the bullet and move forward.
And
what you can. Yeah.
If I, for whatever reason, if I could consider a unilateral case but decide to ignore it for whatever reason, just to see like the calculations, the answer would still be correct because all it serves is to simplify calculation. Okay.
Absolutely. Your answer is approximate when you ignore your S12 always. But when you check whether you can assume it, is that you get a sense of how big your error is going to be. All right. And I'm going to show you now.
The unilateral case implies that there's no feedback, right, in the amplifier. Is that what it means?
It depends, because this is not one directional. All right. Yes, in some ways, if you think a little bit to understand what it means S12 equals 0, the best way is to go to the signal flow graphs. All right, so let me do them here. Just I will do a small thing here. So if you have, this is A, from A, this is A1, B1, B2, A2, and so here, wait. So here is S21, S12, this is S22, and S11. Okay. Let's assume that we have here, so in some ways you are correct in what you're saying. Let's assume that I have a source that goes here, all right? Always the source is gonna go to an A point. And let's assume my source is here, BS. Now, let's assume that I have a reflection here at the end, gamma L, all right? What if my S12 is not 0, then I do have a feedback coming back. You see that? This line.
Right.
Yeah. But if my S12 is 0, and I remove this, there is no feedback. Then I don't know, I don't have any place to go. It does not come back. So in some ways, it's correct what you said. Yeah. Even if in reality, there may be feedback from all other places, all right, that you may have. But this is exactly what it is. Yes.
Okay. I was also like, I remember like from other like analog classes that
Yes.
with feedback, you get better performance in terms of gain and
Except that
stability.
it depends on what kind of feedback you have.
Okay.
If your feedback is positive, then it throws you out of stability.
Right.
But if your feedback is negative, yes, then you may have, you may even improve your gain and everything. Depends on what is the phase. How does your feedback comes together with your input signal? So it depends on the phase, whether it's positive or negative.
Okay. Yeah. That makes sense.
Yeah. Okay. So now, number 1, let us check whether you can assume that the transistor is unilateral. So that's for us, S22 was very small, if you remember, it's here. S12. S12 was this one. The magnitude of S12 was 0.049. So the question is, can I consider that to be 0? So we go here. If you remember, and it is written in the book, we talked about that. There is one figure of merit that we define, and it's this U. And this figure of merit is always a small number. But if you use this relationship here, which we've talked about, then this tells you what mistake you are making by assuming S12 to be 0. Because if you assume that S12 is 0, then instead of the GTU, which is your correct, accurate, if you like, transducer gain for a unilateral, I mean, then what you are assuming, obviously the gain, I mean, your unilateral gain compared to the one you have will be different or will be the same. If they will be the same or they will be very close if your assumption is accurate. They will be different if your assumption is inaccurate. All right. And this is the relationship that you are using to find how far out your assumption is going to make is going to change, how much your assumption is going to change the gain of your transistor. Okay. And then I put here the correct values that we had into U, and what we found for our case, which is different from the exercise in the book. In the book, if you go to the section where in the book, Poser, the author, does the design, the low noise design using the noise circles, the specific transistor he's using, can you assume it's unilateral because the error you make is less than half a dB. But here, the error you make, if you assume that it's unilateral and it's not, is between 1.76 dBs and minus 1.4 dBs, which is huge, all right? So in this particular case, and how do we go from this one here, in case you wonder, how we go from this one down to this one is by taking the 10 logarithm, all right? So you find the 10, you take the 10 logarithm of each part of this inequality. This ratio here gives you this difference and is in dBs. And then here it's that the left part, here is the right part. And it tells you how big of an error you can make. It can be anywhere. So you don't want to make that assumption if your error is so high in dBs, all right? So in our case, unfortunately, we could not assume a unilateral gain for this transistor.
I have a question.
Yes.
What are the acceptable range of error?
Half a dB
Half a dB.
maximum. Yeah.
Thank you.
Half a dB maximum. You know why is that? Because if we go to 3 dBs, that means that you have already lost half of your gain. All right. So if 3 is half of your gain, then you may have to be very close to much well below 1 dB to assume that your error is not that important. So half a dB. Okay. Now, so now we found that we can not use the unilateral, so we'll use all of the full expressions. What is step number 2, we said? Now we have to find how much is the maximum available gain by the transistor. We need to know because they're asking us to do 12 dBs total. And we have no idea how much is the transistor could give intrinsically the highest possible under best conditions. So we need to know that. So we go back to the expressions that you have seen here before. And these are the expressions we are using to find the maximum available gain. What do we do for gamma S and gamma L for maximum available gain? If you want to find your gamma S and gamma L, here you come and find it. You plug in, you only need to have the scattering parameters. You put all of your scattering parameters there, you plug it in, delta, you know how much your delta is? I don't have it here, but it's previously given to us is S12 times S21 minus S11 times S22. That's what it is. And it's in our previous notes. I don't have it here. So if you plug in there, what you find is for this particular set of scattering parameters, the maximum gain your transistor can give is 14.7 dBs. So that tells me that the fact that they're asking me to go close to the noise figure, so instead of 2.5, which is the minimum I can get, they're asking me to go to possibly to go as high as 3 instead of 2.5. But I have enough to compromise in my gain. So that makes me believe that I can do this design. But if my T maximum had been like 12.5, then I would stop here and go back to whoever had asked me and say, you know what, this is not going to work. So before I go and show it to you that it's not going to work, I don't want to do this extra work. I'm telling you it's not going to work. But now, since I have 2.7 dBs difference between the maximum what I have to do, I know it's going to work. Any questions so far? Okay. Now, there is another parameter that I would like to have, which is also useful. And what I would like to know, since I found the maximum gain that the amplifier can give, I would like to show how much is the transducer gain when I have the minimum noise. So practically I define a spectrum of values for G. So I find the maximum that I could go and what I would get for minimum noise. So I know where I am, all right? So I know that I have to be below 14.7. I know that they asked me to be at 12, but how 12, how does it compare to the gain that I would get if I were to get a minimum noise? What if, for example, I'm so lucky that for minimum noise, I can get something close to 12? That will be interesting because I could overdo my specifications practically. Okay, so now I have to find that, and what I do here is to be able to find the GT for minimum noise. We find gamma in and gamma out. All right. For minimum noise, what do? We set our gamma S to be gamma optimum. Remember we said that? And from here, I can find gamma out directly. And from this and the expressions here, I can find G sub S, which is the gain of the input matching network, and that is under minimum noise. Of course, G naught, which is S to 1, magnitude square all the time, and then G sub L. And if I find all of these, then what I calculate here now is that my gain would go to 11 dBs if I were to do a minimum noise of 2.5 dBs. Now that tells me, so far, it tells me that I have a viable solution to the problem. So all of these steps 1 to 3 is to make me confirm that I have a viable solution to the problem, because at 2.5 dBs, so if I were to write it here for you, let me I will add a page here where I am. Okay, step here. I will add a page here. So practically, I have found that if this is a line, it's not a line exactly. And if here I have F and here I have G, okay? If this is F min, then my GT here and F min is 2.5 dBs. Then my GT is 11 dBs. And then on the other end, I have GT max, which is 14.7 dBs. And obviously I have an F, which is much higher than 2.5 dBs. I don't have to find that, but I know they've asked me to be here.
Dr. Kiteki?
1 second, let me finish and then you ask me. They are asking me to not exceed this F value, which is 3 dBs. They ask me not to exceed this one. And they ask me to not have anything below 12 dB. So practically I have to find a place. I have to find a place where I can do this and then I can be below 3 dBs. Yes, now you can ask me.
You said it's 14.7, right?
Yeah, okay, 14.7, I forgot. Thank you. So now I know that I can do that. I can somehow find this value. Okay, I can do this design. I can be less or equal to 3, and I can be more higher or equal to 12 dBs. Okay, so that's all that I've done. And now I proceed with, I continue with the solutions, and what I would like to do is to draw the constant noise circles. Okay, so now I'm doing the work. Now I'm gonna go and do all of the constant noise circles, and then I will put on overlay on them the constant gain circles and see what I get. Okay, now I have to develop the constant noise circles. I go to these formulas and I create a small table. And I suggest that you always do this table so you don't get confused. How do you, each one of these columns is a circle, practically, all right? Because here, for n equals 0, practically I don't have a circle, I only have a point, as you can see, because the radius is 0 of the circle. So I have a point, and this point, it gives me exactly the minimum f, which is in dB is 2.5, but in real value is 1.77. Okay, then I increase n, and I increase n in a modest way because the value of n, the f, I should say f, the center, the position of the center of the circle and the radius are very sensitive to this n value. So I cannot go n equals 2 or 3 because it throws me totally out of the space where I am. But I go from n equals 0, which is like 1 point, and that's the point of minimum noise. I go to n equals 0.15, 0.2, 0.25, and then I can find the centers here, the position of the centers at this level, and then the radius. Okay, so now I do that. Forget about the purple for a moment. The purple is intense, I understand, is a gain circle. But look at the others that we started last time. So look at the blue line, this one. Look at this line. Okay, this line here gives us, in fact, exactly the line on which all the centers of the noise circles will be on. And why is that? Because if you remember the formula, look at this one. All of these centers will have the same phase with gamma optimal. Okay, and that has been given to us by the designer of the transistor. So we know the phase of gamma optimum, and all of the points, they have the same phase for gamma. For reflection, they are on the line. You remember what we said last time? You go on this, along this here. You come here and it's 166 degrees. So this blue line that I showed you has all of the points, and this here, this point here, where was that on? This point is the gamma optimum, which in fact, I will write it again because the other one. Okay, so that point by itself is not a circle, it's just a point and shows where the gamma optimum is. Then I change the values of n, as you can see here, and I'm going to 0.15 and to 0.2 and 0.25. And then you see I selected exactly the one that gave me, it just happened, all right? It just happened to give me something very close to 3 dB. So I selected, instead of putting all of the other circles in place, I selected the one that gives me 3 dBs. And then I know if I draw the 3 dB, which is here, this is the 3 dB circle, all right? If I know that, then I know that every point inside that circle is less than 3 dBs. Is that clear?
Yes.
Okay, perfect.
Something is not for me. How did you get gamma optimum at that point?
It's given to us. Gamma optimum is given by the maker of the transistor. Let me show it to you. Here.
Okay.
So I go and plot it on the Smith chart. How do we plot a reflection coefficient of the Smith chart? We go here. Remember we said you come here.
The second bottom row. The second
Yeah.
bottom row. It's the
Yes, and-
magnitude.
Yes, and you measure and you place it and then you draw a circle, but gamma optimum does not have a circle. So I took the other point, the green one here, which is for the 3 dBs. That's the center. And then I drew the 3 dB circle. All right.
Yeah, understood. Thank you.
Okay. So now, I mean, you could do more circles. If somehow I did not have, who knows? I mean, depending on the problem where they're asking me, but you have to create, my advice will be to create that little table. Because then if you create the table first, then you know how many circles to put. Don't just get the values and then draw a circle. It's going to be so busy that you're not going to be able to know what it is and what it means. So draw this, do the little table first. You will do that both for the noise circles and both for the gain circles. You do the table and then you plot the circles you want. And you plot usually the circle which is going to go closest to the value that you have to design for. Okay, so I got that. We were lucky with this. Now, next step, draw the constant, or did I say constant? Draw the constant gain circles. And gain here. Okay, and so I do that so I can attract your attention because the notes are very long and you may miss something. So we draw these circles, and for the gain circles, we have these formulas. Remember, we found these coefficient G sub S or value, this parameter, which in fact is the ratio between the G sub S that the value G sub S. So every value of G sub of lower GS shows us a ratio of the capital GS over GS max. What is the capital GS? Is the gain of the input matching network and how that compares to its maximum value. Okay, so it's a parameter that we are using. We are using this parameter, and when the parameter has value 1, what does that mean? That we get the maximum value for the input matching network. What happens if we get the maximum value of the input matching network? That implies that we can get the maximum gain for the whole amplifier. Do you agree? Mm-hmm. Yes, because the G sub S becomes equal to GS max under these conditions here, all right? Which implies that we are going to have a conjugate matching on the front, and we always have a conjugate matching at the back. And then one conjugate matching in the front and one at the back gives us total maximum gain for the whole transistor, the whole amplifier rather. So GS1 means total maximum gain for everything. But GS less than 1 means, of course, less than the maximum gain. So all of these circles on the front, all of these ones here, for different values of GS less than 1 will show different circles. And then I did another also similar table where I changed now the GS values from 1, which shows that it's not a circle because the radius now of this circle is 0, so it's a point, all right? So G lower G sub S, when it is equal to 1, your circle for the constant gain becomes 1 point with, of course, 0 radius, and that corresponds to the maximum G sub S on the front end. Okay, and then every other value will give us something different. For every different value of G sub S, I do the same little table here, and I find the centers. Now, what do I know about the centers? From here, if you look, what is the phase? What is the, it's in a polar form, obviously. What is the phase of C sub S as a point on the Smith chart? How am I going to find where this point is? It's going to be on a line that corresponds to what? To the
S11.
opposite, negative.
Opposite. Yeah.
Yes, all right, the phase. In terms of phase, the phase of S11 complex conjugate is negative of the phase of S11. How much was the phase of S11 when they gave it to us? S11 here had a phase of 169. So the complex conjugate of S11 will have a phase of minus 169. Okay, so what I do now, I go to the Smith chart, and now I define, this is the green line you see here, and also I put a note to remember. This green line corresponds to the negative phase of S11. And on these lines, we'll have all of the centers for the purple.
Your audio just cut out. Can you hear us? Because we still can't hear you.
Professor, you show that you're muted on Zoom.
I mean, she only shows muted because she has two accounts, one that does the video, one that does the audio.
And the audio one isn't muted.
Yeah.